Hello students, so we are dealing with the depression in freezing point. So with the help of graph, a similar graph that we already have drawn in an elevation of boiling point. So with the help of graph we can understand easily how the freezing point of solution will be different from the freezing point of pure solvent. So for this we will take x-axis. So this is the x-axis, this is the y-axis. Okay, along the axis we will take the temperature in Kelvin, and along the y-axis we will take the vapor pressure, we may be in atmosphere or bar. Okay, so I will draw here the different curve. Suppose this is the one curve. This is curve AB. So this is for the liquid solvent. This curve is for the liquid solvent. Then from B to C, this is for the frozen solvent. This is for the frozen solvent. Then again I will draw one third curve, that is curve DE. Curve DE. So this curve DE represents the freezing point of solution. Okay. As I told earlier, what is meant by freezing point? Freezing point is such a temperature at which the vapor pressure, suppose this is vapor pressure on the y-axis, the vapor pressure of liquid solvent and vapor pressure of solid of that material will be same. So this point B will represent a common vapor pressure, suppose. Okay. So if we draw a perpendicular line on x-axis, so this will be the freezing point of liquid solvent or pure solvent, we can say, and this point E, from point E, so we will get the freezing point of solution. So from the graph we will get a difference, that is delta TF. So what is delta TF? So delta TF is equal to, that is, we can say it as a diffraction in freezing point is equal to freezing point of solvent, that is TF naught will be the freezing point of liquid solvent, or we can say pure solvent, minus freezing point of solution. So from the graph it is clearly indicated that the freezing point of pure solvent will be more than the freezing point of solution. That means here the freezing point of solution will be less than the freezing point of solvent, and this is nothing but the diffraction in freezing point of a solvent present in the solution. Okay, and this is a very important equation we will get from this graph, and that we will use for the next expression. So now expression for molar mass of solute and diffraction in freezing point of solvent present in the solution. Okay. So here also we will take help of experimental data from experiments. We know that delta TF, that is diffraction freezing point, is also the value of this delta TF also we get from the experiment will be directly proportional to the molality of a solution. Therefore, delta TF is equal to KF into M. So this is our equation number 1. So where delta TF is equal to depression in freezing point, then KF is equal to cryoscopic constant or molar depression point constant of a solvent. Okay, then M will be molarity of solution. Okay, then from the definition, of molarity, M is equal to what? That is N2 upon W1 in kg. That is number of moles of solute divided by, or number of moles of solute dissolved in a 1 kg of solvent. 1 kg of solvent. Here the W1, M1, N1, we are using this term for the component 1 and we are taking the component 1 as a solvent. And W2, N2, M2, that is this component 2, we are taking as a solute component. Okay. So here we got the expression for the molarity. We already know this. That is what is molarity? That number of moles of solute dissolved in a 1 kg of solvent. So here the N2, that is number of moles of solute. Then W1, that is weight of solvent in kg. This word is very important. Okay, but we know that N2 is equal to W2 upon M2. W2 upon M2, where W2 is equal to given weight of solute, M2 is equal to molar mass of solute. Okay, so this is the equation or ratio to get the value of number of moles of solute. So how we calculate it? That is the given weight of solute divided by its molar mass. Then we will get the value of number of moles of solute. So by putting the value of N2 in this equation 2. In equation 2. So M is equal to, what is N2? W2 upon M2 into, then what is left? W1. Okay. So now we will put this value of M in equation 1. Now by putting value of m in equation 1. Okay. Then what is equation 1? That is delta Tf is equal to Kf into m. The value of m, W2 upon m2 into W1 in kg. This is very important. That means suppose m2 is equal to, because we have to calculate the molar mass of solute, so we change the side of this delta Tf and m2. So m2 is equal to Kf into W2 delta Tf into W1 in kg. So this is our star equation. Okay, and this is our equation number, suppose 3. So if you know the value of Kf, that is microscopic constant of solvent, then the weight of the solute, that is diffusion in boiling, diffusion in freezing point, then value of weight of solvent in kg, then we can easily calculate the value of molar mass. Sometimes the freezing point of either solvent or solution may ask, so that time we will use the value of delta Tf. We will use for the delta Tf, we use the expression that is freezing point of solvent minus freezing point of solution. So this is the expression for the diffusion freezing point as well as molar mass, and with the help of this equation we can easily find out the molar mass of given solute. Thank you.